Um, so I'm going to talk about chemodynamics of the Milky Way as reviewed by large observation surveys. I'm from University of Sydney. I would like to thank my collaborators who have helped in this work, Michael, Joss, Dennis, and of course the CLR team. Okay. And Melissa has kind of provided a lot of nice introduction to my talk, but some things will be repeated. Why we are studying the Milky Way, just reminding ourselves, because for distant galaxies, like you see in the Hubble Deep Field, you cannot resolve individual stars, you can only get gross properties. And it's only for the Milky Way that you can resolve individual stars, you can get positions, velocities, age, mass, and so on. So with this, you can test your theories of galaxy formation. And what I want to show is that it's not just a cliche. Now, you can have evolutionary models that you can use to predict most of the properties of the galaxy. And in this context, you can actually interpret external galaxies also now in terms of the processes that work, not just looking at the observations. So that's, I think, the power of using evolutionary models. Just to remind ourselves, so most of the stars in the Milky Way are a disk, and we know there are two disks, like the thin and the thick, and which apparently seem like they have distinct origin and are separate from each other. The thick disk is older, lies high above the plane, and has a higher velocity dispersion. So if you plot in solar neighborhood the velocity dispersion as a function of age, then you can see that there's a break at around 8 to 10 gigayears, suggesting that the thick disk is kind of special and might have a different origin. Now, if you look at the alpha over Fe plane, there also you see this dichotomy, like two sequences, the high alpha sequence and the low alpha sequence with a gap in between, again suggesting something special about the thick disk. But if you, so this is a famous Hayden plot looking at alpha over Fe plane at different R and Z locations. R is increasing along the right and Z is increasing here. So if you look at the topmost slice, which should be the high alpha, if it is thick disk, you see once you go in the outer disk, it becomes low alpha. So the distribution changes as you go in different R and Z. So it's not that simple to interpret just by high abundance or to say thick disk is one thing. There's a lot, trying to study the disk is like trying to study an elephant blindfolded, and depending upon where you look, you get very different answers. Thinking about alpha poor, is it thick disk, or what are the mechanisms, migration, and so on. An eye-opener in this case, I think, is the ability to get ages for a large number of stars. And there are two types of stars, the main sequence turn of stars and the giants, for which you can get ages. And that's because if you are using turn of stars, the isochrones nicely separate each other. So you could measure just from isochrones the ages. But for giants, you have to rely on astroseismology to get the mass, because mass is correlated with age, or you can use carbon and nitrogen abundances. And the other eye-opener is the fact of radial migration. Like earlier models didn't take that into account, and it was very difficult to predict a lot of properties. But once you put radial migration into your models, a lot of these seemingly difficult properties become much easier to explain. And of course, with Gaia, we now have phase space information for a large number of stars, and spectroscopic surveys are now giving you ages. And with huge amount of data, we can finally actually fine-tune our models and understand like the physical process that govern them. So the aim of the talk is to actually reproduce this Hayden et al. Plot from apogee data and try to understand this, why this double sequence arises. Is it because of the distinct thick disk? Is it related to the pause in star formation specifically? So the model, basically it has two main parameters or variables. One is the age and the other is the birth radius. And we are assuming that the abundances are homogeneously mixed along the azimuth. Now, if you take the probability distribution of age, that's the star formation history, which is shown here by the orange line. It rises and then it falls off gently. And for the disk, we assume an exponential disk, but the scale length is allowed to vary with time. That is, it's an inside-out formation. And this has a subtle effect on the plots. It's not necessary to get the dichotomy, but it does help to have better agreement with the data. And for the chemical evolution, we adopt an empirical approach where we prescribe as to how the function should be as a function of birth radius and age. and similarly for alpha, and then we fit that to observational data. Okay, so now let's imagine a ring or stars born at a certain time with a given birth radius. They would be in the form of a ring. And if you ask the question, where are they now? Well, the first thing is radial migrations would spread them around, their guiding radius would change. And the second thing is that they get scattered by different scattering processes and they get heated up. So they have velocity dispersion. So that means they are scattered both in the Z direction and in the R direction. So they end up something like in a torus kind of a region. So to understand the distribution of stars now, you need to understand the velocity dispersions, specifically how they vary with L, birth radius, and age. So I'll take a short digression to understand the fundamental relations that govern the velocity dispersion of stars. So what are the fundamental variables that could be responsible? Well, age, of course, because scattering processes increase the dispersion with age. Traditionally, radius has been used, but I would argue angular momentum is a better variable. That's because it's a constant of motion. And if you want to construct a distribution function of system in equilibrium, it should be a constant of motion. Then we have the metallicity, because for a given age, metallicity gives you birth radius. And finally, we have height above the plane. And we put this in because we saw that the data actually demanded something like that. And I'll talk about that later. So what kind of functional form we should choose? Well, I adopted a very simple functional form just to see if it works, and it worked pretty well. It's just multiplicatively separable functional form. That means the dependence of one variable is independent of the other, and they are related by a product form. Now, it happens many times that you get some result with one survey, and then you try to do that with a different survey, and you don't get the same answer, or you use one kind of tracers to measure ages, and you measure ages with something else, with a different tracer, again, you don't get the answer. So we used two different surveys here, Lamost and Galactic. We use main sequence turn of stars, and also we use red giants employing carbon and nitrogen abundances for measuring ages, and also astroseismology from the K2 mission to get the ages. Now, to visualize this multivariable problem, what I'm going to show is when I want, so suppose you want to study the dependence of X, I divide the velocity by a quantity over here, which encapsulates the dependence of other variables. For example, if you want to study age, you can take out the dependence of all the other variables and look at the dispersion of this with age. So now I'm showing the velocity dispersion as a function of different variables. The top row is for vertical dispersion. The bottom one is for the radial dispersion. The first column is angular momentum. And the different lines out here are different surveys, going from Lamos, Gala, and Red Clump, and K2, and so on. So for the top one, what you see is there is a gentle, there's an exponential fall, and then there's a rise. And for VR, you see a fall, and then there's flattening. Now with age, you see in general a power law rise. The black lines here are analytical fits that are used in the model. And of course, the slope is larger for VZ. Then with FEH, it's a linear fall, and similarly with Z, there's a linear. So one thing to note here is the different surveys and different tracers, they all give kind of consistent answer, which is good. Old and young all lie on the same line. So the thick disk is nothing special, like we saw in the solar neighborhood. There was a break from the power law, and that was because you didn't take the other variables into account. But if you take all the variables into account, all of them, thick disk or thin disk, they lie on the same relation. So some things were not expected here, like this rise with L and this dependence on metallicity and Z. Now the dependence on Z is most likely because the disk is not in equilibrium, as suggested by Macrath et al., because the spiral arms are close to the plane, and they drive most of the scattering. It takes time for that to propagate upwards. For the dependence on other variables, I'm going to talk in more detail now. This dependence on L, well, the exponential fall here was expected from theory if you want a disk that has a constant scale height. And this flattening again is expected if you think stars are born with a finite birth dispersion, and that could be because the gas from which they're born is turbulent and has some finite dispersion. But this rise is difficult to understand. And in simulations, actually, you see that, and it's most likely because of orbiting satellites, because in the outer disk, the self-gravity is less, and the orbiting satellites can perturb more, the vertical motion can be perturbed more easily. Now, for the dependence on age, there's a long history going back to 1953, when GMCs were predicted as one of the main scatterers. So giant molecular clouds, they can do scattering and induce this dependence on age, but the exponent or the power of the power law is predicted to be 0.25. And in general, what it was found was the heating rate was too low. So then other mechanisms were invoked, and one of them is the transient spiral arms. So a combination of spiral arms and GMCs works quite well, but the spiral arms can only give in-plane scattering, and the GMCs are still required to get you vertical scattering. And in a nice paper by Omer and Binney, they were able to show that the GMC fraction actually decreases with time, and this actually helps explain the overall low heating rate that we are getting. So now that's not a problem. And also the exponent turns out to be 0.45 correctly. Okay. Now for the dependence on FEH, which was not expected again, so what we see, FEH is anti-correlated with birth radius in our models, right? And the dependence that we see in our data, what that suggests is that sigma V, or dispersion, increases with birth radius. Now, how can that happen? Let's imagine stars in the solar neighborhood and think about inward migrators shown in red. So when they come here, they have higher dispersion shown here, and the outward migrators, they have lower dispersion. And this is what the data is telling us. Now, how can that be? Well, one of the things that can do that is the conservation of vertical action, which was shown in Solvay. So if you have conservation of vertical action, it can explain this. But if you think about the dependence on L, stars in the inner disk are hot to begin with. So what that means is, if you want this result as shown here, stars, the migrating stars must be preferentially cooler because they are very hot here, and only the cooler ones, when they come here, they will decrease afterward, conservation and so on. So, and in simulations, this has been shown to occur. It's called the provenance bias. Okay, so after covering the velocity dispersion, I'm going to come back to chemical evolution. So like I said, it's an empirical model. So you think of different annular rings. For example, this is the solar radius. So this plot shows the evolution of metallicity with time, and the bottom one is evolution of alpha. So if you focus on the red line, you can see the metallicity increases over time and then flattens out. And for alpha, it's a similar case. It's high and then it falls and flattens out. Now, this flattening might be related to different processes that reach some kind of an equilibrium between chemical enrichment and inflow of fresh gas. I guess Chen will talk in his talk more about chemical models, and he can explain. So we prescribe these kind of models, and the sharp fall here is very important for the double sequence that we see, and it's basically due to the time delay between the star formation and the onset of supernova 1A. So it can be predicted from that. So now we use observational data from Galactic to actually fit these models. For example, for alpha, you can see this dependence with a birth radius, or FEH, is shown here. And then if you track the evolution, the dependence on age is shown by the green line from Galactic and the best fit model out here. So having calibrated this model, we now go on to make the predictions for the distribution of stars in the alpha over Fe plane. So this is for the solar annulus, a little bit above the plane, like 1 to 1.5 kpc. And we can easily see the double sequence here. The model correctly predicts it. Now, to understand this plane, is better to think of different evolutionary tracks. Now, these different tracks out here are for different birth radius, going from 1 all the way to 14. This is the inner galaxy 1 kpc. And as you go leftwards, you see the different tracks there for different birth radius going towards the outer disk. And the dots here show you the different times. So this is starting at 13 gigayear, 12, 11, 10, 8, 4, so on. So if you know
5 minutes.
If you know the birth radius and time, there's a one-to-one mapping in the alpha over Fe plane, right? So one thing to notice here is that this high alpha sequence, so-called, is actually a sequence in age. You see the age is changing along this. And the low alpha sequence is basically a sequence of birth radius. And this huge spread that you see is because of radial migration, because all these stars are in the solar neighborhood, and the only way they can come from here is by radial migration. Now, this is the apogee data. Now I will make the prediction of show the model predictions for all of stars in the RZ plane. I'll flick a few times just to see how well the model is doing in predicting the data. I mean, some details are not perfectly matched, but overall, the basic features are very well reproduced by the model. And some interesting things like the inner galaxy is basically this one sequence over here. So the blue line here is basically an evolutionary track for birth radius of 4 kpc, and the orange line is for the local birth radius. And in the inner galaxy, it's just one. All of them lie on the local birth radius. And if you look in the top slice here, you can see it's high alpha, and then as you go towards the outer disk, you see the low alpha, just like it was seen in the data. And that's because of flaring. If you remember, velocity dispersion was increasing with L, and that was the cause for flaring. And that's what actually causes this thing here to see. If you don't put in radial migration, this is what you get. This doesn't look like the observational data at all. The low alpha sequence is not spread out at all. And most of the stars just lie on this orange line, which is expected because they're not migrating. Okay, so we showed that alpha elements can be predicted from just age and metallicity. But just like we heard in Melissa's talk, she did with the apogee, you could predict other alpha elements and other iron peak elements. So in Galab, we also had the S and R process elements. And now we'll look for 23 elements in Galab. And we found that all the elements, if you just take the age and metallicity, both from MSTO stars and from the K2 astroseismic ages, you can predict all the elements with 0.03 dex. So this again brings up the question of what's governing this. So what's the reason for this? Well, one of the reasons obviously is there's strong azimuthal mixing happening in the disk. And this tells you that the mixing processes are quite strong compared to the stochastic nature of dispersing the enrichments like from a supernova. We can hear more about this on Michael's talk. So that brings to my conclusions. I guess I have a few minutes. Okay. So what I've shown is that a simple chemical evolution model can explain in detail the abundance distribution at different R and Z locations. So we now understand the origin of the double sequence and the fact that the migration is important in explaining this. And you don't need a pause in star formation to explain this. Even the uniform star formation rate, you can reproduce the double sequence. We learned about the fundamental relations of velocity dispersion, especially the fact that orbiting satellites might be important for explaining the rise of sigma with L that we saw. And there's conservation of vertical action and also provenance bias, that migration is more efficient for cooler stars probably. And we learned about how scattering by GMC and spiral arms can explain the dependence on age. Finally, most abundances can be predicted just from age and metallicity. And so to look forward in future, like I was saying in the beginning, what this tells you that now you can explain the galaxy in terms of evolutionary models. So you can take the properties of the galaxies and link them to physical processes. And I think this is very important when you look at external galaxies, for example, M31, and you see the alpha over Fe plane, you could immediately say why this doesn't match with Milky Way, what processes are different, and so on. Okay, that brings to the conclusion of my talk.
Great, thanks, Sanjib. Perfect timing. We have a couple questions in the chat already. Corinne, do you want to unmute and ask your question?
Yes, good morning. Thanks for this very nice talk. I was wondering if the fact that stars die and expose their yields at a different place than their birthplace is taken into account or not yet when you actually plot, for example, alpha over iron at as a function of time at different radius. Is this yield release at different place taken into account?
So in the mod, if I understood correct, you were saying if the fact that they were born at different radius, is that taken into account in the final plots that I made, right?
The fact that they actually release their yields, they die and release their yields at a different place than their birthplace.
Oh, okay. No, I think so the first part of the model didn't make any assumption about how the mixing happens. So it just assumes that the ISM is azimuthally homogeneous and the abundances only vary as a function of radius. So that was an assumption in the model. And so it has nothing to do with what the real mixing is. But in reality, yeah, those questions are very important for understanding why the spread in abundance is so small, or all the abundances can be expressed only in terms of age and metallicity. There, this mixing process, like if what you're saying is true, that mixing happens at different radius, that would certainly change some of the conclusions, and we should see more dispersion, I guess. But do we expect, so like the supernova ejectors, they are supposed to go up to 50 parsec. Do we still expect the enrichment to be more, the correlation of that to be more than that? Do you have any physical process in mind that could explain why ejector goes far away from the birth point?
No, I don't know. It was just a question, actually.
Okay.
Yes,
yeah, I think if you take supernova, like they have the most energetic explosions, and like what's the maximum radius they expand to before everything is mixed and collapses back again? I think that number is something like 50 parsec, if I remember correctly. So we argue that in the paper, there's an argument based on that.
Yes, but they moved more than 50 parsec from their birthplace.
Oh, that's
okay. Yes,
yeah,
maybe we can. Yeah. Maybe we can talk about. Yeah.
Yeah. I think it would be azimuthally more mixed in that case. Yeah.
Perfect. Okay, Nadej, do you want to ask your question?
Yes, thank you. I have a question about the young alpha-rich stars, and if you can predict these stars, and because we can observe these stars in different surveys like Apogee and the compilation with Apogee and Kepler. So, could you explain these stars or not?
Could you say that? Could you repeat your question again?
Could you explain the young alpha-rich stars we can observe in different surveys?
Okay, young alpha-rich stars. Yeah.
Yes.
Yeah, nothing in my thing. I'm just trying to think. Okay, so the young alpha-rich stars are very small in number, and that didn't affect any of the conclusions that I presented here. But I mean, I think a lot of them probably are just because the uncertainty from astroseismology is about quite large. So my gut feeling is a lot of them are actually just because of uncertainty and they are not real, but some of them could certainly be real and probably related to some other exotic mechanism like binaries or things like that. Does that answer your question?
Yes, but I think some of them are real because you have a different paper in the literature that can demonstrate that the ages deduced from astroseismology is quite accurate for these types. So
I agree. I mean, so some of them certainly are real. I'm not saying that they're not real, but a lot of them could also be false positive. Like in K2, I think in the data that we looked, there were a significant number of stars that were young alpha-rich. It was difficult to say. We didn't follow up anything with more detailed investigation as to how many of them are real or not. But that's certainly interesting to follow up and see. It's good. It would be important to know the answer to that. Yeah.
Okay,
thank you
very much. We need to move on. So if there are a couple other questions and comments in the chat, feel free to move those to Slack. Thank you, Sanjib, again.